Hello, so in this video we will talk about introducing what planar graphs are. So let's start as usual with the definition. A graph is planar if it can be drawn in such a way that no two edges cross except at the vertices. So we have earlier, so K24 we have seen that looks somewhat like this. Okay, so we see that there are so many crossings here. Now can we draw this graph so that these crossings can be avoided? The answer to this question is yes. So we can do something like this. We can say 1, 2, 3, 4 here, 1 here, and 1 here. And then we can say this, this, and this, and this, and this, and then this, and then this. So this is my group 1, and this are in my group 2. So this is a planar representation. Okay. So similarly, we can draw an arbitrary. Let's do another example. So for example, we have something like this, a hexagon. Okay, and then we have a vertex like this, edge like this, edge like this, edge like this, edge like this, and edge like this. Okay, now note that in my drawing only the last two edges created the problems, right? So I can just draw this graph the same order, but this one, this edge here, I can draw it like this, and this edge here I can draw it like this. So this is another representation of the same graph. Okay, so this is non-planar representation and this is a planar representation, and a graph which can be drawn in a planar representation is called a planar graph. Okay, so it turns out K24 is planar and this guy is planar. Okay, so now the question is that can we um, can we have a statement or a theorem or something which can be shown to prove or disprove whether a graph is planar or not? I mean, this is just inspection, right? We can just for example, you will see that K33 is actually not planar. But how? So we need to know some concrete statement so that we can use that statement to prove or disprove whether a graph is planar. Okay. So now for that we need to define a terminology which is called regions or faces. Okay. So in a planar graph of a drawing, set of points that are not on the graph are divided into faces or regions, and one of those faces is always infinite, and the degree of regions is the number of edges encountered in the walk around the boundary of a region, and the degree of region also fulfill the handshaking lemma. Okay, so let's draw this guy. So we know that this is a planar representation. Okay, so let's draw this guy again. We have 1, 2, 3, and 4, and 1 and 2. Okay, so this goes, this goes, this goes, and this goes, and then this goes, and this goes, and this goes, and this goes. So this is my R1, this is my R2, this is my R3, and this is my R4. Okay, so this is my first region, this is my second region, this is my third region, and the outside is my fourth region. Now note that what is the degree of R1? We have, if we now let's start walking around the boundary of R1. So 1 edge, 2 edge, 3 edge, and 4 edges. Similarly for R2, 1, 2, 3, 4. R3, 1, 2, 3, 4. R4, 1, 2, 3, and 4. So this is region, degree, regular, with degree 4. Okay, so region degree regular or face degree regular means that each region has the same degree. Okay, now this also fulfills the handshaking lemma. So handshaking lemma says what? That the sum of degrees, so we say I, and let's say we have R regions, so this is degree of Ri, this is equal to 2 times our number of edges. Okay, now note that again, our, as we have been doing, graph is always defined by a set of vertices and set of edges. Okay, so now once we have defined this story, now let's go to the Euler's formula. Okay, Euler again here. So Euler's formula says that in a plane drawing of a connected graph, the number of vertices v, the number of edges e, and the number of regions r always satisfy the following. So this is what we have, what Euler actually came up with. Okay. So the proof of this requires induction. Induction on edges, that also works, and some places you will also see induction on faces or regions. Okay, that also works. Okay. Okay, but we are more in this video, I'm more interested in the application of the Euler's formula. And remember, our goal is to find a concrete statement so that we can prove or disprove whether a graph is planar or not. Okay, now the application is, this is what I'm really interested in. So this says that in a simple connected graph with shortest circuit length of C, um, so this is number of edges is always given by C times V minus 2 divided by C minus 2. Okay, and proof of this story relies to on how the degree of regions relate to C, and we will see this proof. Okay, so let's say that we have shortest circuit length of C. Okay, now the question is, what is the shortest circuit length has to do with the region? And note that circuit is what? A cycle, right? We start with this, we start with some vertex and end up with, move around the graph and end up with the same vertex. So how many edges do we encounter is the same as the boundary of that region of the path. So this means that shortest circuit length is usually equal to shortest degree of regions or minimum degree of regions. Okay, so now using this story, now let's start with the um, handshaking lemma here. So what did we say? We said that I, this is equal to 1 to r, degree of Ri, this is equal to what? 2 times E. Okay, where E is this E. This E is the same as this. Okay. Now, since every Ri, degree of Ri is greater than C or equal to C, so I can say C times, so this, let's say this is small r. This is small r because this is small r. So C times R. So now I'm replacing this guy by something which is smaller, right? So then this means that this is less than 2 times E. Okay, or I can say R is less than 2 times E over C. Okay, now I go to this equation again. So this equation says V minus E plus R is equal to 2, and then I can say V minus E plus 2E over C. Now I'm replacing R by something which is greater than R, right? So this should be greater than 2. Okay, and then it's just um, algebra. So there is some algebra here, and algebra means you just have to bring this E on that side and do some factoring out of some terms and bring it on the other side. So then you can say, you can end up with easily E is less than c times v minus 2 divided by c minus 2. Now let's look at the examples here. Now we have k5. K5. So K5 looks like this: 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So now, what is E? We have, I think I missed one, right? Okay. We have how many edges? We have 1, 2, 3, 4, 5 edges. What is V? V also is 5. Okay. What is the shortest circuit length here? What is C? So 1, 2, there is a triangle. So there is nothing which is less than 3, right? I can see some triangles here. So C is equal to 3. Okay. So now let's check what is C times V minus 2 over C minus 2. So which is equal to 3 times 5 minus 2 divided by 3 minus 2, which is equal to 3 times 3, 9, 9. So what is E? How many edges do we have? No, edges not 5, edges is 10. Okay, because 5 here and 5 there. So edges is 10 and it should be less than or equal to 9 for it to be having a planar representation. So this means that K5 is not planar. Now let's move on to K33, for example. Now K33 looks like this: 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, and 3. So what is C here? So first of all, what is E here? So E is equal to 3, 3, and 3, 9. V is equal to 6. What is C here? What is the minimum length of a circuit here? 1, 2, 3, 4. It's a bipartite, right? So it has to be even here. Okay, so now let's calculate again C times V minus 2 over C minus 2. This is equal to 4 times 6 minus 2 over C minus 2. So 4 times 4 is 16 divided by 2 is 8. So this is 8. And my E is 9. So 9 is greater than 8. So therefore, this is also not planar. Okay. Now we talk about another graph which is called the Peterson graph. Okay. So the Peterson graph looks like this. We draw a star first and then we have one here, one here, one here, one here, one guy here. So this, then this, then this, then this, and then this. Okay. So now what is E? So E is equal to, so we have 5 here, 5 here, and 5 here, 15. V is equal to, we have 10 edges, so 10 vertices. What is C here? So do I see a triangle? No, I don't see a triangle. I do have a pentagon here, so it is, it is 5 or less. So do I see anything for 4? So 1, 2, 3, no. So 1, 2, so this is an inspection part here. So 1, 2, 3. So you can see that C is 5 here. Okay, so let's again calculate C times V minus 2 over C minus 2. So this is equal to 5 times 10 minus 2 over 5 minus 2, which is equal to 5 times 8 is 40. 40 divided by 3 is 13.33. And E is more than that. Therefore, this Peterson graph is also not planar. Okay. So in summary, what we did was we defined our planarity of a graph, and then we moved on to the regions, and we said what does a degree of a region mean, followed by Euler's formula, but most importantly we checked the application of Euler's formula based on this region and the degree of region story, and we said that okay, if we have this story, then can we check whether a graph is planar or not? Yes, now we can check. But note that if this condition is whole, so if condition holds, it still does not confirm anything because it's not an if and only if statement, right? So this is very important to know that we can go backwards, but we cannot go forward here. So it does not guarantee, it may or may not be. If this condition does not hold, then definitely we cannot find a planar representation. But if the condition holds, then there may be or may not be a planar representation. Okay. So now, before we finish, in a simple graph, connected graph, there exists at least one vertex with degree 5 or less. Okay. So we use contradiction and we assume that all the vertices have degree at least equal to 6. Okay, so then uh, using the handshaking lemma, we say degree of vi sum, this is equal to 2 times the number of edges, correct? Okay, and since all the degrees are more than 6, then the sum of all the degrees should be greater than 6 times v. So we can say 2e is greater than 6 times v, correct? Greater than or equal to. Okay, so then we say that e is greater than 3 times v, correct? Okay, and then remember that we have e is less than this guy. So the minimum value of c is 3, the minimum value of v is also 3. So this guy says e is less than 3 times v minus 2. Okay, and this says equal to 3v minus 6. Okay, so this guy says e is less than 3v minus 6. This guy says e is greater than 3v. So this means they both cannot be true at the same time. Okay, so this means that there must be at least one vertex with degree 5 or less if planar graph, correct? Because otherwise doesn't make sense, right? So it's a simple connected planar graph. There exists at least one vertex with degree 5 or less. Okay, so this is it about this topic, and hope you like the video. Thanks for watching.